Hello everybody, in this video we are going to start a revision on solid state. As we know that the basic distinction between solid, liquids and gases is molecular motion. And molecular motion is more restricted in liquids than in gases, and in solids the atoms and molecules are packed even more tightly together in well-defined positions. And solids, they are generally characterized by their high density. So solids are generally characterized by their high density. It's high density and low compressibility. Now, these two properties are something that keep solids apart from liquids and gases. Now, the magnitude of these properties for solids is an indication that the constituent species are closely packed together. So, a high density means that in a present volume, more number of particles are present as compared to the substance which has got low density. Therefore, high density generally is the characteristic of solids. Okay. Now the solids, they are divided into two categories known as crystalline or amorphous solids. These are categories are crystalline solids or amorphous solids. They are crystalline solids or amorphous solids. Now, amorphous solids are the solids like glass. They lack a regular three-dimensional arrangement of atoms. Therefore, if I draw the diagrams of crystalline and amorphous solids, they will look like this. Suppose a proper arrangement is there of different types of ions in any material. They are the characteristic of crystalline solids. Suppose this represents cation, just suppose, and this represents anion. Now, as you can see that there is a proper arrangement of cation and anion in this diagram. So this is the characteristic of crystalline solids. Whereas if this diagram is somewhat more randomly arranged, then this will be the characteristic of amorphous solids. Suppose anion is there and there is cation, then there is another cation, then there is anion. There is no any particular order. Okay. So this is what represented generally by amorphous solids. Suppose this is so they have low range order. Amorphous solids. Therefore, by looking at this diagram, we can say that crystalline solids have long range order, while amorphous solids have short range order. The long range order here means that the atoms or ions or molecules, they are arranged in a regular fashion. Like here in crystalline solids, these atoms or ions are arranged in a regular fashion, whereas in case of amorphous solid, this is not the case. Therefore, we say that here the order is very short ranged. Here in this case, amorphous solids case, the order is very short ranged, but in the case of crystalline solids, the order is a long range order. And also, because of this, crystalline solids have sharp melting point, while amorphous solids have diffused melting point. So, the properties we can write here: long range order, sharp melting point. Okay, sharp melting point means they have a specific melting point. Okay, whereas in case of Amorphous solids, they are short range order, they have short range order, and they have diffused melting point. Diffused melting point. By diffused melting point, we mean that there is not a specific melting point in case of amorphous solids. And there is another property for crystalline solids, and it is that crystalline solids are anisotropic, while amorphous solids are isotropic. This is the case of liquids and gases. Like liquids and gases, amorphous solids are isotropic. For example, glass. Okay, isotropic, it means that the value of any physical property like diffractive index, conductivity, etc. measured in different direction is same, since they are homogeneous. Okay, so hence we can write as amorphous solids are they are isotropic, while crystalline solids are they are anisotropic. Okay. Now, since we have studied the properties of crystalline and amorphous solids, now since they are characterized by high density and low compressibility, so they are arranged in the form of cell. A solid is always arranged in the form of cell. For example, there is nothing like 1 meter of a single unit of a solid. Okay, there is one smallest unit which makes a large unit with the assembly of their identical particles. Therefore, the smallest repeating unit of a crystalline solid, is called unit cell. Unit cell is always in the form of cube. Okay, a unit cell is always in the form of cube. Suppose this is the case. Okay, so this is the case of a unit cell. Numerous unit cells combine together to form a particular solid. Okay, now a unit cell are characterized by different properties. There are different types of unit cells. Suppose I give different types of nomenclature to different parts of this unit cell. Suppose this length is B, this length is C, this length is A. Suppose I say that here the length is A, this length is B, and the height is C in this particular unit cell, and this angle is beta, this angle is alpha, and this angle is gamma. Let's visualize this. You should have a good visualizing power in order to visualize it in 3 dimensions. Therefore, it is advised that please give us time or spare a little amount of time to visualize different types of structures that we'll be discussing throughout the chapter. Okay. So, according to Brevis was a scientist who studied this unit cell or the structure of solids in great detail. According to him, 3 vectors and 3 angles study shows
morphologically that the unit cells can be classified into 7 crystal systems based on the presence of certain rotation axis. Okay, so there are total of 7 crystal systems in case of unit cell. Okay, and remember, please try to remember these 7 crystal systems, because one complete question of 8 marks, that is matrix match type question has been asked based on the table that we are going to draw right now. Okay, so please make sure that you remember this structure, remember the system that we are going to write or we are going to draw here. So let's write here crystal system, and here intercepts, and here crystal angles. Here angles means alpha, beta, gamma. Here crystal system, the name of the crystal system, and intercepts are the relationship between A, B and C. Okay, so the first crystal system is cubic, which is the simplest form of unit cell. Cubic, its intercepts are A equals B equals C, and angles are related by alpha equals beta equals gamma equals 90 degrees. Other is orthorhombic. In this case, all 3 intercepts are different, but the angles are same. Alpha equals beta equals gamma equals 90 degrees. Rhombohedral, this case A equals B equals C, but alpha equals beta equals gamma not equal to 90 degrees. There is another type known as monoclinic. In this case, all 3 are different to each other, but alpha equals gamma equals 90 degrees, but beta is not equal to 90 degrees. There is triclinic. A not equal to B not equal to C, and alpha not equal to beta not equal to gamma not equal to 90 degrees. So most disarranged structure is the triclinic one. Remember the conditions for a structure to be triclinic, that is A is not equal to B not equal to C, alpha, beta, gamma all different to each other, and the value is not equal to 90 degrees for any of them. It's tetragonal. A equals B not equal to C, alpha equals beta equals gamma equals 90 degrees. And there is another and last type, it's hexagonal. A equals B not equals C, and alpha equals beta equals 90 degrees, gamma equals 120 degrees. So remember this table. One complete question has been asked which carried total of 8 marks, so, based completely on this table. So please go through this table thoroughly. Okay, now in IIT JEE we only have two crystal systems in syllabus, of which only 4 Brevis lattices exist. Okay, so in IIT JEE we have only two crystal systems in syllabus, for which only 4 Brevis lattices exist. Thus we have to study only in syllabus. We have to study only primitive or simple cubic, primitive or simple cubic, body centered cubic, face-centered cubic, and hexagonal primitive. Face-centered cubic, and fourth is hexagonal primitive. Now, suppose the first case, when the body is of primitive or simple cubic. Suppose the first case, primitive or simple cubic. Now this structure will look like this. This structure will look like this, simple cube. Okay, there will be nothing inside. There will be nothing inside this cubic structure or anything or anywhere other except for the corners one. This is the simple cubic structure. Now to study further, we should study about two terminologies named as rank of a structure, okay, and the relationship between A and R. This signifies the relationship between A is the length of this structure, suppose the side length is A, and R is the radius of the atom. R is radius of atom. Radius of atom. So two terminologies are rank and packing fraction. And packing fraction. Okay, so rank is the number of atoms in one single unit cell. Okay, so the total number of atoms in one single unit cell is known as rank, and the packing fraction is the total amount of relative volume occupied by the atoms inside a unit cell. Therefore, in primitive or simple cubic, there are a total of 8 atoms occupying the corner of each cubic cell. Now, one atom is shared by a total of 8 cubic cells. Now, if you can visualize it, suppose there is an atom, and this is the equator of that atom. Okay. Now, this inner part or the area which is below that equator, it is shared by 4 unit cells. If you look at it closely, and if you visualize it, then you will see that you will come to a conclusion that 1/2 is shared by 4. 1/2 of an atom is shared by 4 cubic cells, and therefore 4 cubic cells are shared by the other half of this atom, and therefore total number of at corner one atom is shared by 8 cubic cells. Okay, and hence in this case rank equals 1/8 into 8, and since there is no other atom anywhere, therefore it equals 1. Hence total number of atoms in one simple cubic unit cell is 1. Okay. Now if you take this area into consideration, let's take one particular area into consideration. Let's take these 2 atoms into consideration. Then we will see that the atoms are arranged like this. This is one atom, this is another atom, there is the radius r, here radius r, and the total distance is a, that is length of the side of this cubic unit cell. Hence we can say that here a equals to r. Therefore radius of atom equals a upon 2. Now to calculate the packing fraction, the total amount of volume occupied by one unit cell is a cube. We know that total volume equals a cube. Okay, and the volume occupied by
occupied by atoms equals total number of atoms, that is 1, into volume of one atom, that is 4 upon 3 pi r cubed. Okay, hence packing fraction equals 4 upon 3 pi r cubed upon a cube, or we can write it as 4 upon 3 pi r cube upon 2r whole cube. So if we solve it, we'll get the value as 0.523. Therefore, packing fraction is 0.523. And hence packing efficiency, if you multiply this packing fraction by 100, then we get packing efficiency equals 52.3%. So this is for simple cubic unit cell. Now let's study about body-centered cubic structure. Now in case of body-centered cubic structure, or BCC structure, body-centered cubic. Now one atom is there inside the body. Okay, so this is since this is the cubic unit cell, one atom is there at the center of this unit cell. Okay, now total of 8 atoms are there at the corner, plus 1 atom is there at the center of the unit cell. Therefore, rank in this case equals 1 plus 8 into 1 upon 8. Therefore, here rank becomes 2, and packing fraction or packing efficient or packing fraction, or before packing fraction, let's see what is the relationship between radius of atom and the edge length. Okay, so since here in this case atoms are arranged like this, this is the center atom, this is one corner atom, and there is another corner atom. So this constitute one diagonal, and this is A, and one diagonal equals 4r. Okay, so from here we can say that 4r, that is one diagonal, 2r from this atom, and 1r from this atom, and 1r from this atom. So therefore total 4r equals the length of diagonal, and the length of diagonal is root 2a. Okay, so length of diagonal is root 2a. So from here, now in this case, here, okay, this is not equal to root 2a, this equals root 3a. Now, if you visualize it in 3 dimensions, then you will see that if this equals a equals root 2a, this diagonal equals root 2a, or the hypotenuse equals root 2a. Now, if you extend it to 3 diagonals, into 3 dimensions, now this equals root 2a. Now, if we draw a right angled triangle taking this hypotenuse, taking this edge length, and the body diagonal, then we get body diagonal, that is L square equals root 2a squared plus a squared. So from here L equals root 3a. Okay, so in this case it comes out to be 4r equals root 3a. So from here value of r is root 3a upon 4, and from here packing fraction comes out to be 0.6802 units, or packing efficiency equals 68.02%. Okay, so there is another type known as FCC, or face-centered cubic structure. The third is FCC structure.
Now in this case, in FCC structure, only the atoms are present at corner and the center of the faces. Atoms are present at the corner, at the corners here, and at the center of faces. Okay, so if you visualize it, you'll get to know about the structure, and you can easily find out that here rank in this case equals 4, and here A equals 2 root 2 R, and so packing fraction, it comes out to be 0.7405. Therefore packing efficiency equals 74.05%. Now since we know that density of any cubic crystal, equals density of cubic lattice. Now if we take it to the unit level, then this becomes equal to the density of unit cell. So since density equals mass of unit cell upon volume of unit cell, so from here if we simplify it further, density comes out to be total number of atoms in a unit cell into molecular weight of that particular species that under consideration upon Avogadro number, because this will be the mass of one unit or one atom. So N into M upon Avogadro number is the mass of one atom. So this constitutes the mass of one atom into volume. So this is the density of unit cell, N into M upon N into AQ. Okay. So now let's study about hexagonal primitive structure. So let's study about hexagonal primitive structure. Hexagonal primitive structure. Now, this hexagonal primitive structure, they are arranged somewhat like this. The atoms are arranged here like a hexagon. Now, above this level, 3 atoms are arranged. Now, above this level, there is another hexagonal structure arranged in a similar fashion. So, we can call it as A, B, A type of structure. Because because this layer and this layer, they can be superimposed upon each other. Therefore, both of these layers are same. And since B is different from A, therefore it has been named differently than A. Hence, we can call it as A type of structure. Now, the coordination number of each atom is 12. In this case, coordination number of each atom equals 12. The fraction of unit cell, therefore fraction of volume of unit cell occupied by atoms is, or packing fraction, equals 6, since 6 atoms are there in this in one unit cell, into 4 upon 3 pi r cubed upon area of base into height of unit cell. height of unit cell. Okay, so the distance from A to A is C. Therefore, height becomes C by 2. Now, if we do a little bit of mathematics here, we will get the value of C equals 4R under root 2 upon 3, where R is the radius of atom and A here is the edge length, which equals A equals 2R. Okay. Now, therefore, area of base is calculated by the area of 6 equilateral triangles. Now, just look at it closely. You will see here 6 equilateral triangles at the base. Therefore, area is simply the area of 6 equilateral triangles. Therefore, area of base comes out to be 6 into root 3 by 4 into A squared. Okay, now if we substitute all of these values in packing fraction, we get the value of packing fraction as 0.7405, or packing efficiency equals 74.05%, which is same as that of FCC structure. So we can say that FCC structure and hexagonal primitive unit cell, they are the most efficient type of structures. Okay, so let's discuss something about void. Void is nothing, just similar to its English meaning. It is the empty space that is left inside any structure. We can call it as void. So there are two types of voids that we study here. Voids, they are the empty spaces. So there are two types of voids known as tetrahedral voids. Tetrahedral void, and other is octahedral void. Octahedral void. Now, if you just look closely, that if we arrange 3 atoms here in this fashion, okay, so in this fashion, okay, now there is some empty space in between. There is some empty space in between, right here. So if we put one more atom here covering this empty space, then now just flip this arrangement, you will see some empty space in the vicinity of these 4 atoms. Okay, so if you look at it closely, or if you look at it carefully, and if you join the centers of all 4 atoms, you will see that a tetrahedron has been formed. Therefore, this void is known as tetrahedral void. Now, in this case, suppose the radius of the atoms are RH. These atoms, we call it as host atoms, which are forming those type of voids. And suppose the atoms which are getting infilled in those voids are the foreign atoms, and they have the radius as RF. Suppose radius as RF of foreign atoms. And these are host atoms. Generally, host atoms are cations and foreign atoms are anions, because cations are greater in size than that of anions. So, in case of tetrahedral voids, RH, radius, sum of radius of host atoms plus foreign atoms equals root 3a by 4. This can be proved very much easily if you apply a little bit of mathematics knowledge, an elementary level of mathematics knowledge, just like we did in calculating the packing fraction or the radius in in the previous parts, or in simple cubic structure or body centered cubic structure. So in case of tetrahedral voids, this is the case RH plus RF equals root 3a by 4. Now, here, in general, the number of effective tetrahedral voids in a unit cell is double the number of effective atoms in that unit cell. So in general, the number of effective tetrahedral voids in a unit cell is double the number of effective atoms in that unit cell. Okay, now in case of octahedral voids, if you arrange octahedral voids, if you arrange 3 atoms like this that we arranged earlier, now if you arrange 3 more atoms but in opposite order, if you arrange 3 more atoms here in opposite order, or so that you can see it. Now, if we arrange 3 other atoms here like this, here like this, now there is a void formed in between with the intersection of the void of upper layer and the lower layer. Now if you join the centers of these six atoms, you will see an octahedral shaped void, and hence this is known as octahedral void. Now in this case, RH plus RF equals A upon 2, where A is the edge length, and in general the number of octahedral voids equals the number of effective atoms, equals number of effective atoms. So these were the concept of voids. Now let's discuss something about radius ratio. Now since we just now saw that generally that host atoms are cations and are anions, and the foreign atoms are cations, because in case of anions their size is bigger than that of cations. Therefore there is a concept of radius ratio. It equals radius of cation upon radius of anion. This is nothing but the ratio of the radius of cations to that of radius of anions. So there are different types of structures that we study based on the type of voids, and also our basic understanding of structure as primitive or simple cubic or bodies. Cubic known as rock salt structure or zinc blende structure shown by ZNS, fluoride structure, anti-fluoride structure, cesium halide structure. We'll come across them in the form of questions as we'll solve questions. And let's discuss something about defects. Now, as we know that nothing is perfect in this universe. So we know that nothing is perfect, therefore everything has got some of the defects. We study those type of defects in different area known as crystal defect. Now, since till now we have assumed that all lattice structures were perfect or ideal, therefore we got all the values as perfect for example, values of packing efficiency or the relationship between radius and the edge length. Okay, but in real practice, crystal lattices have substantial number of defects, and these defects affect the mechanical, electrical, and optical properties of the solids. Okay, now the lattice imperfections, they are classified according to their geometrical characteristics. These are crystal defects of 4 types in such lattices. So there are crystal defects of 4 types. Crystal defects of 4 types in lattices. 4 types in lattices. First is vacancy, defect due to vacancy. Second is self-interstitial. Self-interstitial. Third is substitutional impurity. Substitutional impurity. And fourth is interstitial impurity. Interstitial impurity. Okay, now if an atom is missing from a lattice site, it creates a vacancy. And due to vacancy, density of the crystal decreases. And due to absence of atoms, some lattice sites, the occupancy of the lattice sites decreases, and the percentage occupancy of such crystals can be determined as, so in this case, percentage occupancy can be determined as observed density upon theoretical density into 100. Okay, so under these types of lattice defects, under these types of crystal defects, there are various types of subdivisions of the defects have been formed or have been named. Now, if an atom leaves its lattice site and occupies some other interstitial space, then the defect is referred to as self-interstitial. Due to this defect, density of crystal remains unaffected. Now, in case of self-interstitial defect, density of crystal remains unaffected. And if a foreign atom displaces or substitutes a host atom and occupies its lattice site, the defect is called substitutional impurity, because substitution has taken place here. Okay. And such defect can alter the density of crystal depending upon the mass of replacing atom relative to replaced atom. And if the foreign atom do not occupy a lattice site but occupies some interstitial space, then the defect is referred to as interstitial impurity. Due to such defects, the density of crystal increases because the number of atoms has been increased. So, to summarize all these defects, let's draw a diagram. Suppose these are the atoms of a particular solid arranged in this fashion. Okay. Now, if this atom from here, it gets missing and it occupies some other place. Suppose this, it occupies some other place. So this atom goes missing and it occupies this place. Therefore, this is known as self-interstitial. Self-interstitial. And suppose this atom, it gets replaced by another atom. Suppose this atom, it gets replaced by another atom here. So this is known as substitutional impurity. Substitutional impurity. Okay, and if there is no change in the number of atoms in any structure, but one foreign atom has occupied some interstitial site in this structure. Therefore, this is known as interstitial impurity. Interstitial impurity. So, the type of crystal defects in a lattice made up of atoms only, this is what we have shown here. Now, let's consider these crystal imperfections in ionic crystals. Now, a vacancy at a cation site is mostly accompanied by a vacancy at a nearby anion site. Such paired cation-anion vacancies are referred to as Schottky defect. Now, paired cation-anion vacancies are called Schottky defect. Now, in this case, density of crystal decreases. Density of crystal decreases. Okay, but it maintains the electrical neutrality of the particular solid. But maintains electrical neutrality. There is another type of defect known as Frenkel defect. It is a type of defect when an ion, whether it is cation or anion, leaves its lattice point and occupies the interstitial space. Okay, just like self-interstitial. So this can be shown by Frenkel defect. This can be called as Frenkel defect. Okay, so in this case, an ion leaves its lattice point and occupies some interstitial space. So in this case also, electrical neutrality is maintained, but and the density remains unaltered. So in Frenkel defect, density remains same. Okay. Now let's discuss some of the questions here. Now the first question says that the unit cell of aluminium is a cube with edge length 405 picometer. The density of aluminium is 2.70 gram per centimeter cube. What is the structure of aluminium crystals? Okay. Now since we know that density equals N into M upon Avogadro number into A cube. Okay, so therefore from here N equals rho, that is density, into Avogadro number into A cubed upon molecular weight. So from here N equals 2.70 into 6.023 into 10 raised to the power 23. Edge length is given to us as 405 picometers. So converting in centimeter, we get 4.05 into 10 raised to the power minus 8 cubed. We have converted 405 picometer as 4.05 into 10 raised to the power minus 8 centimeter. So 4 cubed upon 27. Because the density was given to us as 2.70 gram per centimeter cube. Therefore, every new unit has to be converted as grams and centimeters. So from here, value of N comes out to be almost equal to 4. Therefore, since the rank of face-centered cubic is 4, we can say that the unit cell of aluminium is face-centered cubic. Okay, so let's discuss another problem. And the question says that spinel is an important class of oxides consisting of two types of metal ions with the oxide ions arranged in CCP pattern. The normal spinel has 1/8 of the tetrahedral holes occupied by one type of metal ion and 1/2 of octahedral holes occupied by another type of metal ion. Such a spinel is formed by zinc, aluminium and oxygen with Zn2 plus in the tetrahedral holes. Give formula of the spinel. Okay, so since this, let's discuss about the first part only. Now, since it is given in the question that oxides that important class that the normal spinel has 1/8 of tetrahedral holes occupied by one type of metal ion and 1/2 of octahedral holes occupied by another type of metal ion. Now, since zinc occupies the tetrahedral holes here. Zinc occupies tetrahedral holes here, and the number of oxides, as we know that it is occupying just the corners and the faces of the cubes. So therefore, since this is an anion, therefore FCC structure or cubic closed packed structure, oxides should occupy the main positions and the cation should occupy the voids. And hence, number of oxides ion is number of oxide ion per unit cell equals 1/8 into 8 contribution from corner species or corner atoms plus half into 6 from face centered atoms equals, so therefore number of oxide ions becomes 4. Now number of zinc ions equals, since zinc ions is occupied by tetrahedral, since tetrahedral voids are occupied by Zn2 plus ion, therefore number of Zn2 plus ions per unit cell equals 1/8 into 8. So this value comes out to be 1. Because it is given that 1/8 of tetrahedral holes are occupied by zinc. Okay, so and now since 1/2 of octahedral holes are occupied by aluminium, so therefore number of aluminium ions per unit cell equals half into number of octahedral holes, which is equal to the number of effective atoms, therefore equals 4. So this equals 2. So the total number of tetrahedral holes are the twice, then that are the twice of the number of the effective atoms, that is 2 into 4 equals 8, so 1/8 equals 1, so the total number of Zn2 plus ions per unit cell is 1, number of Al3 plus ions per unit cell is 2. So therefore from here we can say that the formula of spinel is Zn Al2O4. So this is the answer. Now the second part of question is asking us that if all the species in problem A touch each other, determine the fraction of volume occupied by ions in the unit cell. Now for FCC lattice, since 4 radius of 2 negative equals root 2a, we had studied it before. So from here, radius of oxygen 2 negative comes out to be root 2a upon 4. Now for octahedral voids, for octahedral void, since RH, for octahedral void, since RH, that is radius of host plus radius of foreign atoms equals a by 2, we had discussed it a few times before. So therefore RO2 negative plus RAl3 positive equals a by 2. This is host atom and this is the foreign atom. And for tetrahedral voids, for tetrahedral void, RO2 negative plus RZn2 positive equal root 3 A by 4. So from here we get the value of, since A equals 2 root 2 R O2 negative, and therefore R2 O2 negative plus R aluminium 3 positive equals root 2 R O2 negative. So from here, if we substitute the value of A as 2 root 2 R O2 negative, so we will get this expression. So from here we get the value of A R radius of aluminium 3 positive equals root 2 minus 1 R O2 negative. So this comes out to be 0.414 R O2 negative. Okay, and now similarly radius of Zn2 plus, it comes out to be 1.255 R O2 negative. Okay, so now here so this plus R O2 negative, this comes out to be 1.225 R O2 negative. So from here radius of Zn2 plus is 0.225 R O2 negative. So packing fraction, therefore packing fraction equals 4 total number of oxide ions into 4 upon 3 pi R O2 negative whole cubed plus 1 into 4 upon 3 pi 0.225 R O2 negative whole cubed. This is the case of zinc, plus 2 into 4 upon 3 pi 0.414 R O2 negative. This is the case of aluminium, upon A cube, that is 2 root 2 R O2 negative cubed. So after solving it, we get the value of packing fraction as 0.77. Therefore packing efficiency is 77% approximately. Okay, so this is the packing fraction of the volume occupied by ions in the unit cell. The answer is 77%. So let's move on to another question. The question says that a strong current of trivalent gaseous boron passed through a germanium crystal decreases the density of crystal due to part replacement of germanium by boron and due to interstitial vacancies created by missing germanium atoms. In one such experiment, 1 gram of germanium is taken and the boron atoms are found to be 150 ppm by weight when the density of germanium crystal decreases by 4%. Calculate percentage of missing vacancies due to germanium which are filled up by boron atoms. Okay, so in this case, we have to assume here that the decrease in density is not due to volume change but due to loss of germanium atoms only. So therefore let total number of germanium atoms equals X, which are missing. So hence to write it clearly, total number of germanium atoms missing equals X, and the number of boron atoms replacing germanium ions, number of boron atoms replacing germanium atoms are Y. Now assuming the volume of crystal remaining same, then 4% decrease in density will also decrease weight of crystal by 4%. Okay, since the volume is same, hence if 4% of density has been decreased, therefore 4% of weight of the crystal has also been decreased. And hence, from here, we can say that 4%, it simply means that 0.04 of the relative amount. And hence, X into molecular weight of germanium, that is 72.6 upon Avogadro number, minus Y into molecular weight of boron upon Avogadro number equals 0.04. Okay, so here Y equals nothing but 150 into Avogadro number upon 10 raised to the power 6, since 150 ppm was given in the question, into molecular weight 11 into 0.96. So therefore, from here the value of Y is, so from here Y into 11 upon Avogadro number is 150 into 0.96 upon 10 raised to the power 6. Okay. So therefore, if we substitute that value in the expression that we got earlier, so from here 0.04 equals X into 72.6 upon Avogadro number minus 150 into 0.96 upon 10 raised to the power 6. So from here, if we simplify it further, we get the value of X as 0.04 into Avogadro number upon 72.6. This value is approximately. Okay. So if we divide Y and X here, since Y here is this, Y here is this. So if we divide this Y and X, so if we divide Y by X, then Y by X will come out to be 150 into N AV into 0.96 into 72.6 divided by 10 raised to the power 6 into 11 into 0.04 into NAV. So from here, Y by X comes out to be 2.376 into 10 raised to the power minus 2. Therefore, we can say that Y upon X into 100 equals 2.376%. So whatever the question was asking, that calculate percentage of missing vacancies due to germanium which are filled up by boron. So only 2.376% of vacancies were filled by boron. Okay, so let's discuss another question. The question says that the edge length of unit cell of a metal having molecular weight 75 gram per mole is 5 angstrom. Which crystallizes in cubic lattice. If the density is 2 gram per centimeter cubed, then find the radius of metal atom. The value of Avogadro number is given to us as 6 into 10 raised to the power 23. Now give the answer in ppm. Now since we know that density equals total number of atoms into molecular weight or atomic weight upon Avogadro number into volume. So from here, N equals rho into Avogadro number into volume upon atomic weight. So if we substitute the values further, we get the value of N as 2 into 6. The value of Avogadro number is given in the question as 6 into 10 raised to the power 23 into 5 into 10 raised to the power minus 8. We have converted the value of edge length in centimeters, not in meters. Please take care in mind, because density was given in gram per centimeter cube upon 75. That is the molecular weight was given in the question, 75 gram per mole. So from here, value of N comes out to be 2. Okay, and now since R equals root 3 by 4 into A, Because since edge length is cube, therefore this is a BCC structure. BCC structure. So in case of BCC structure, R equals root 3a by 4. So from here, value of R is root 3 by 4 into 5. Edge length was given as 5 angstrom. So from here its values comes out to be 2.165 angstrom. Or since or converting it in picometer, because it is given in the question that give your answer in picometer. So the value comes out to be R equals 216.5 picometers. So this is the required answer. And this question was asked in IIT JEE 2006. Okay, so let's discuss another problem. And the problem says that the crystal AB, which exists in rock salt structure like NaCl, has molecular weight 6.023 yAmu, where y is an arbitrary number in AMU. If the minimum distance between cation and anion is cube root of y nanometer and the observed density is 20 kg per meter cube, find the density in kilogram per meter cube and type of defect. Now density here equals, has molecular weight as 6.023 y. So density here equals 4 into 6.023 into y upon 6.023 into 10 raised to the power 23 into 8 into y into 10 raised to the power minus 27. Because here edge length equals 2y 1 by cube 1 by 3. Because minimum distance between cation and anion is y raised to the power 1 by 3. Therefore, from here edge length can be made out to be equal to 2 into y raised to the power 1 by 3. Okay. So, and it is the property of a rock salt structure. Density will be 4 into 6 in 6.023 into y, because here n equals 4. Here n equals 4, and this is the volume. Okay, so since edge length equals 2y raised to the power 1 by 3, so therefore volume will be y 8 into y, because a cube will be 8 into y. Now converting this nanometer into meter, this will be 10 raised to the power minus 27. Or if we just elaborate it, if I do it, since we know n into molecular weight upon Avogadro number into volume. So here A equals 2y raised to the power 1 by 3 into 10 raised to the power minus 9 meter here, and n equals 4 because the structure is rock salt structure, and m is given to us 6.023 into y. Okay, so from here, since y and y will get cancelled, from here density comes out to be 5 into 10 raised to the power 3 gram per meter cube, or equals 5 kilogram per meter cubed. So the density has been calculated, and now we can see that density which has been calculated is smaller than the density observed. Now since density calculated is smaller than density observed, therefore the defect is metal axis defect. Therefore defect is metal axis defect. And this question was asked in IIT JEE 2004. Okay, so let's move on to another question. The question asks us that an element crystallizes in FCC lattice having edge length 400 picometer. Calculate the maximum diameter of atom which can be placed in interstitial site without distorting the structure. Now in FCC, interstitial sites will be octahedral voids and tetrahedral voids. We already know this. Now in case of octahedral voids, for octahedral voids, R1 upon R2 equals 0.414, and for tetrahedral voids, R1 upon R2 equals 0.225, where R1 is the radius of atom in interstitial sites and R2 is radius of atom arranged in FCC. Okay, so therefore that is, so from here, which implies us that 4R2 equals root 2A, where, or if you should write it, that R1 equals radius of atom in interstitial sites, and R2 equals radius of atom arranged in FCC. So since this is the property of FCC, that 4R2 equals root 2A, so for maximum diameter of atom in interstitial sites, octahedral voids will be considered for maximum. So this will be considered. Okay, so from here, diameter equals 2R1 equals 2 into 0.414 R2. So from here, diameter, it comes out to be 2 into 0.414 into 400, that is the edge length, upon 2 root 2. So this comes out to be 117.1 picometer, and this is the answer. This simple question was asked in IIT JEE 2005. Okay. Now let's discuss one more very easy problem. The question says that packing efficiency of the two-dimensional square unit cell shown below is, okay, so there are total number of 5 circles. Now we have to calculate the packing efficiency of the unit cell, and the unit cell is found by connecting the centers of each of the circles. Okay, so the packing efficiency of this region. So packing efficiency, as we know that packing efficiency will be area of, this will be, let's do it on the other page. Here packing efficiency will be area occupied by circles divided by total area So area occupied, since there are total number of 5 circles in total, but in this unit cell we can see that there is one circle which is at the center. This circle is completely in this unit cell, and each outer circle contribute 1/4 of the area to the unit cell. Okay, since each outer circle is contributing only 1/4 of the area to the unit cell, therefore total number of circles in the unit cell will be, here n will be 4 into 1 upon 4 plus 1. So n will be 2. Total number of circles will be 2. And if the edge length is A and the area of circle is R, so if radius of circle is R and edge length is A, this L equals A. So in this case, A equals 2 root 2r. Okay. Here A will be 2 root 2r if we consider this portion. This will give us the value of A. Here 4r equals root 2a. So from here A equals 2 root 2r. Now therefore packing fraction, so this efficiency will be if you multiply this packing fraction into 100. So packing fraction equals 2 into pi r square, because two circles are there and they have radius r. So area of one particular circle is pi r square upon simply a square. A square is 2 root 2r whole square. So if we solve it completely, we will get the value of packing fraction as 2 pi r square upon 8 r square. So this will come out to be pi by 4. So the packing efficiency is pi by 4. Now so packing fraction is pi by 4. So if we multiply it by 100, packing efficiency equals pi by 4 into 100. So this value will come out to be 78.54%. So therefore the correct answer is 78.54%. And this question was asked in IIT JEE 2010. Very easy problem. It was asked in IIT JEE. So let's discuss one last problem. And the question says that the arrangement of X negative ions around A positive ion in solid AX is given in the figure, not drawn in scale. Okay, so figure, if the radius of X negative is 250 picometer, the radius of A positive is, okay, so figure here is given to be as, this is one layer, this is other layer, and this is one more layer. The hexagonal structure that we discussed during discussion of octahedral voids. Now, beneath this layer, there is one other layer of the atoms, which if we look at it from above, it will look like this. There are 3 layers beneath this proper layer of atoms. Okay, so this is X negative. And there is one atom here in between, so this is A positive. Okay, so the radius of A positive we are required to calculate. Now according to given figure, A positive is present in octahedral void of X negative. From figure you can find out that this void is octahedral. So A positive is present in octahedral void of X negative. Now the limiting radius in case of octahedral void is related to radius of sphere as our void equals 0.414 sphere. So from here our A positive, it comes out to be 0.414 Rx negative. Rx negative is given to us as 250 picometer. Therefore radius of A positive is 0.414 into 250 picometer equals 103.5 picometer. So the correct answer is 103.5 picometer. So it can be rounded off to 104 picometers. So the correct answer is 103.5 picometer or 104 picometer. So this question was asked in IIT JEE 2013. Very easy problem, just recently asked. So that's all for this chapter. See you in the next chapter.